Okay, so we are all here to study about networks. And I'm going to talk about a specific type of network that hydrologists have studied for decades. That's river network. And as we know, river network is one of the kind of network we have basically studied most deeply. And the learning we have achieved for decades have significantly influenced the wider community of network science. So hopefully, in the next 20-some minutes, I would like to give you some very extracted abstract of what we have achieved during last decades about river networks. So let's go I'll take you to the journey to the network. Okay, through our journey, we'll first take a look at the topological organization of river network. What does it look like? And then we'll look at the hydrological function. And we talked about evolution, but we'll also look about evolutionary dynamics here. And I'll talk about the insights for the future research. Okay, so river, what is river? Basically, river is an excellent mechanism that drains raindrop toward a certain point, which we call outlet. So you have all the raindrop fallen within certain area, we call the catchment. And how do you drain all these raindrops? Let's say this is catchment, then basically it's a connectivity problem. Let's say you divide this catchment equally spaced nodes, and let's say this black one is outlet, your goal is to arrive there. And if I give this question to elementary school students, show me your creativity, how do you connect all these points? They may give me different answers, right? Maybe you can connect all these points in this way, spiral pattern. Maybe some students can connect them in this way, explosive pattern. Maybe some students connect in this kind of branching pattern. Okay, then what are river networks look like? Is it look like this, or like this, or like this? So this is a river network, Gyeongsangang River in Korea. As you can see, obviously river network shows branching structure. I'm not showing this example as intentionally, but we know that if you examine river networks anywhere, on this planet, Asia, Africa, North America, Europe, Australia, no exception. They all show branching structure. I have never seen a spiral pattern network or something. That's not network, by the way. It's not just branching. If you look at small part of river network here, for example here, it looks similar to bigger part, right? So there is some concept of scale invariance. So it has been known. Okay, so if you take a small part of river network and zoom in, it looks similar to this original one. And if you repeat this again and again, so it basically river network is good example of vector showing self-similarity. So then, what are the quantitative measures of self-similarity? We can go all the way back, Horton's legendary work in 1945, Horton's law, which is about the ratio between, according to this ordering, the ratio between the number of streams, etc. And Lex law and so on. Since 1980s, with the availability of a digital elevation model, now we can do more. We can do a lot of different types of terrain analysis. For example, if you have this kind of given digital elevation domain, so these numbers basically, in this just example, indicate elevation field, you can actually estimate what should be the flow direction, like this way. So as you can see, this example indicates one single catchment, one network, and from this you can extract for each point what is the contributing area, like this. And then we were interested in, okay, if you choose one point in a random manner, what is the probability that the point will have certain value of range area? Okay, you can make a PDF. And you can also plot exceedance probability distribution with that. Surprisingly, the exceedance probability distribution shows straight line on log paper. So we call it power law. As we can see in any other physics examples, we see power law as a good indicator of sample similarity or scale invariance, meaning that the process happening at smaller scale is repeatedly occurs at greater scale at the log scale. And what is also interesting here is that this scale, free domain, they show some slope. In this case, that's around 0.43, slightly smaller than 0.5. And if you analyze many river networks, they are small, within very narrow range. Okay, so if you analyze network in tropical region or Arctic region, they show similar scale invariance property. We call it as a hierarchical density, actually. Why this is important? Because this is actually, you can see from general networks point of view, equivalent to what we call size distribution. Okay, size distribution, and we call it as a scale invariance. This is a hierarchical density. Then there can be interesting questions such as why river networks have this kind of very narrow range of hierarchical density. What are the density of the other networks? Are they all fractal? And so on, right? So we can test this idea by testing by some kind of algorithmic approach. We can make theoretical study like treating a topological structure as like a string. So the idea is basically you assign an ID number for each node. And for every node, there are only two classifications. One is whether you have children, like this one, whether you have no children. If you have children, you have index number 1. If you have no children, index number 0. And you narrate this index number according to your ID. Then this topological structure can be written as a string like 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, etc. So that's this one. So we can replace tree topology as a simple string. What we can do with this one? With this one, we can actually theoretically test what is the influence of random kind of perturbation within the deterministic structure in the converging topological organization. For example, we can start from very deterministic structure. So you can see here, this is repetition of 1001, 1001. This is very deterministic structure. I don't know what this topology look like yet. And there is another pair, which is completely randomly generated pair. Let's say its randomness is 0, its randomness is number 1. And let's say if you want to take partially random network, we can choose, let's say about 20%. You can choose about 20% of total digit. It has 19 digits, so 20% is about 4. You randomly choose 4 digits and swap those numbers with totally random tree. Then this is a new string which is based on the deterministic structure, but you have about 20% randomness. What does it look like? You can test this from a little bit bigger example. So starting from 0 to 1, 0 to 1, and gradually increasing the randomness, the corresponding tree topology varies slowly like this. So if you start from strictly self-similar tree, it slowly, as you add random component, gradually changes to this state. If you start from this one, this is completely, it is not self-similar. This is a good example, which is not fractal. This is self-repetitive tree, which is like a backbone of, and doesn't follow power law. But if you add a little bit of randomness, you already start to show tree structure, which is very relevant. Now, what are their theoretical density? We can try and see whether they follow power law, and we surprisingly see that as randomness grows from 0 to 1, in most cases, except this place, they follow power law. Okay, so we can say statistical self-similarity is an inevitable consequence of any full binary tree organization. Another interesting point is that in the case of strict self-similar tree, if you add randomness in the string, you keep this theoretical density almost steady, up to 80%. What this means is you have a string, you have a kind of basic structure, and you mix up to 80%, okay? 80% of that. But still you keep your original inherent structure. So that's very resilient. So that's what we know about topological organization. Then what are their functions? We know that ribbon network organization is strictly related to its response. So let's say your network is, this is not network though, you have something river like this, the response will be like this. With the same number of nodes, if the organization is changing like this, the response will be different. And if you change it again, the response will be different again. We call this as a topological width function, or shortly width function. Basically talking about transfer of water from upstream to downstream. But in the real case, you have to think about dispersion effect too, because in the previous case, you actually has a linear transfer from distance to time. But what happens is actually there is a dispersion. So what you can solve is, if you want to really want a good solution, you have to solve one-dimensional advection dispersion equation here. Well, actually, Andrea Rinaldo and others has proposed very convenient equation. Approximate solution of this one is given as like this. This is travel time distribution, which is widely used. And using this idea, you have two parameters here, the dispersion coefficient and celerity, which can be estimated through some measure of depth of water, velocity, and slope. They can be also measured from hydraulic geometry relationship. So this comes to the importance of hydraulic geometry relationship. Not just network geometry is important, but also hydraulic geometry is important in terms of function of the network. So what have we found with this framework? So one of the examples is we can address some issues of known nonlinearity problem. So this is a well-known figure from Winshaw's 1960 paper. So you have actually derived unit height graph for different rainfall events for the same watershed. They are completely different, right? This is completely, so they say the conventional unit height graph theory is problematic. And you see that the time to peak and peak discharge is well following the rainfall excess rate. So if you think the original unit height graph theory is correct, there should be just straight line like this one. But how can I formulate this with this new approach? Well, this is calculated instantaneous response function according to the network topology plus hydraulic geometry. You can clearly see that the same pattern we have seen in the catchment. Another good example is actually done by Water and Rinaldo. If you just repeat this topological width function from real catchment, what you can usually see is something like this. That is negatively skewed distribution. But we know the hydrologist response should be supposed to usually positively distribution. Why is it different? So they have found that basically the hill slope is plays important role. So the key difference in celerity between hill slope and channel plays, make it shifting the skewness of the total distribution. And this is a following study by Snell and Sinapalan. Actually, they repeat the same importance here. Okay, now let's take a look at the evolutionary dynamics and how this river network has formed. Actually, there is very important role of climate and geology, and there are two processes of fluvial processes and geological uplift processes, which driven the landscape changing to certain different state. If you go into detail, we can talk about very detailed ways of governing the formulations. But simply speaking, the governing equation is very simple. It's just talking about conservation of mass. So you have this time change of elevation at specific point, and you have a spatial change of sediment flux. This term is tectonic uplift term. So we are talking about fluvial processes and geologic processes. To close this equation, you need some supplementary equation for QS. Sediment flux can be usually written as power of slope and the discharge. With this, we usually simulate landscape evolution in 3 steps. You extract stream networks first, and you simulate fluvial processes, and you simulate non-fluvial surfaces such as soil production and tectonic uplift, and goes back. So let me show you some example of landscape evolution simulated by our model called LEX by my former student. You can see here the valleys formation and network development from this. You can actually take a look at the transect of this example learn. You can see how the topography changes within one transect. And an interesting point is network formation. If you look at how the network forms over time, okay, I hit the wrong button, all right. If you look at how the network forms over time, let me show from here. Okay, see, the network forms very quickly at the initial stage, and it becomes very stabilized quickly. Okay, that is property of network development in the wider sense. In a repeated simulation, we see the same patterns in any cases. So, insights from here. Maybe not limited to river networks, we can apply same principles to other types of networks. This is actually Google Earth image of the tidal network in western coast of Korea. Very similar mechanism, but the difference is you are not draining rainwater. This is driven by water drainage, driven by tidal elevation differences. What we explained the formation about these river networks in our earlier work with myself and Praveen Kumar was that there is an inherent role of randomness, which plays crucial role. And we find that randomness plays same role in other systems here, like all physical systems. There is elevation energy gradient here, potential energy gradient. In these examples, there is electric energy gradient, and the media is not completely pure. There is always inherent randomness. So, in that case, you can see network structure forms, and the evolution time scale is very short. In this one, if you impose random shock of energy, you have immediately get this kind of rectangular figure. And here is a lightning. It's very short time scale. This is another ball bearing experiment which forms a self-organized network formation. There is another types of networks, very similar to river networks, but found in the biological system. Kevin showed an example of loops network of leaf, but here let me take, we can talk about that later, but let's talk about simpler case without loop. So leaf is essentially very similar to river network, and if you think about its version to animal, that's a vascular network, blood vessel, very similar branching structure. And if you look at the external body, we can also think about feather. So this is all result of evolutionary process over time. So feather, for example, has been maybe evolved from something like my hair, which has just one string, and they start to have branching structure. Then why do they prefer branching structure? If you think about physical system, they prefer branching structure because of inherent randomness, control it. Here, maybe the survival strategy, natural selection, okay? So maybe different mechanism. So this is an area which needs future research direction, I hope. So what we have learned about river network organization, we see ubiquitous self-similar topological organization, which can be quantified through power laws. I can expect similar patterns in other types of networks, such as urban drainage network. And its hydrological function is strongly related with topological structure. So we can apply same idea for the transfer of mass energy information of any network. And its evolutionary dynamics, our current stage is we can computer simulate what the evolution look like. Actually, now we are coupling this my former simulation with Kevin's model about vegetation, etc. And insights with our lessons from river network, maybe we can explore mysteries of more general complex networks. Thank you very much.